All right, good morning, everyone. So let's get started with the seventh lecture of the Dark Matter School. And I'm going to continue from where I stopped last lecture, which was around there. So I'm going to recap again, as always, recap a bit of the key aspects that we discussed in the last lecture. So we discussed some of the things we learned from drug detection experiments on the experimental side. And I just want to revise some of the key things we learned. Okay. So first we learned that different targets are needed, and that has to do with the minimum velocity, which is needed to produce a recoil at different targets. Okay, that's lesson number one. Lesson number two is that typically dual phase readout techniques are needed to offer a better handle on the background or on the signal over background ratio. Why? Because as you're going to see again, I'm going to emphasize for the xenon detector, dual phase techniques have a way to better discriminate signal from background. And we learned that lesson from Cogent, where Cogent had just one readout technique, which was just ionization. And they did it on purpose to reduce the energy threshold. Third, we learned that fiducial volume is assumed for every single direct detection experiments to avoid surface events. We also learned a lesson from Cogent. We learned that direct detection experiments need to be placed underground to suppress somehow the large volume the incidence of cosmic rays, right? Because we saw that the muon flux, I think it's here, somewhere below. Let me see. The muon flux reduces greatly as you go underground. Let me see, it's there. Yeah, there. The muon flux, the cosmic ray muon flux is reducing. That's why you go into around 2,000 kilometers underground, water equivalent. So that's the unit that's relevant for underground measurements. Okay, let me go back. And we learn also the quenching factor is important because the quenching factor tells you how you can correlate the ionization energy to the actual energy which is deposited as a whole into the nucleus. Okay, that's the ratio. And the sixth lesson we learned is that the energy threshold of the detector limits how small the dark matter mass you can probe at a given detector. Okay. In the seventh lecture, we're going to learn today that the dark matter scattering is not elastic for large momentum transfer. Okay, we're going to learn this today. So let me continue from the xenon. So we reviewed the germanium detectors. Now we're going to go through the xenon detector. So this is a cartoon picture of the xenon detector where it's surrounded by several materials. And just towards in the middle, we have a tank of xenon gas and liquid, so dual phase xenon. And today we have about 8 tons of xenon, but we started with 10 kilograms, and now we have 8 tons of xenon. And the goal is to go around 20 tons of xenon. That's what we require. Okay? So I'm going to just go through this paper today. So I advise you that if you want to be a dark matter expert, I really strongly advise you to read the experimental results, experimental papers. So they really dive into the details of the dark matter detection technique. So this is a paper from March this year. First results from nuclear recoils searches using xenon and ton. So it's 7 tons of xenon. Had actually more than 7 tons, but the fiducial volume was equivalent to 7 tons. Okay, so they had more than 7 tons, but the fiducial volume was 7 tons. And there are more than 100 authors in this paper. So from March this year. So we are in 2023, and we are discussing a paper from March this year. So let me try to explain how it goes. So this picture on the right is the actual picture of xenon detectors. There's 3 stores, 3 floors detector, the whole thing. On the right, you can see all the technical technical equipments, the readout techniques, and so on, the wiring, electronics, etc. The systems they use to subtract the background events, the krypton background, which is the most relevant nuclear background for xenon detectors currently. And the way it goes is the following. So this picture you can see here is not an empty space. It's just like a flag. They put it on top of the xenon tank. So this whole tank there. And remember, just inside there is a small tank with 5 tons of xenon, and it's compressed. So it's not a huge volume. It's just really compressed xenon because they want to increase the density to increase the chances of having a scattering. Okay? It's a purified xenon. So the way it goes is towards the top of this figure, you have a gas phase of xenon, which is, remember, xenon is a scintillator. And you have an electric field, a node and a cathode to drive an electric field, okay? So in this case, the electric field is pointing downwards. And on top and in the bottom, there are photomultipliers. And this signal you can see here on the top in red. So right there, let me see here. Let me use. So this one here in red is like if a signal of dark matter signal was produced around here, the electrons will be drifted upwards, reach the gas phase. This gas phase will emit light, and these photomultipliers will pick up the light. And then that distribution of light in the photomultipliers will tell you, will inform you where exactly in the position, the 3D position of your detector, where that event took place. So the red signal means that's concentrated around the red, and the way you go further away from where the event took place becomes yellow and then goes almost green and then goes to white. So it means that in this figure that the event probably occurred around here. So you draw a line right there. So occurred anywhere in this red, yellow in the detector. And then, okay, you just know this map that's occurred around the vertical line. But depending on how long it took for the light to arrive at the photomultipliers, then you know the depth of the tank, and then you know you have now a 3D position of the event in the detector, okay? So here you get an X and Y in the plane of the circle. You have an X, Y position, the Z position, which is inside into the plane. Then you know from the time it took for the electrons to arrive to produce light. So it's a 3D mapping of a signal. Okay. And let me just show you that the key things for xenon detectors are the S1 and S2 signals. So S1s, I'm going to explain what they are soon enough. So you have two signals, S1 and S2. S1 has to do with the electrons, which are just already removed as soon as the nucleus, the neutron or some neutral particle comes in, hits the whole xenon atom, and then bounces and strips off some of the electrons. These electrons are called S1 signal. Those electrons are drifted and reach the photomultipliers, and then produce another light. So this is S2 signal. So xenon sees light, period. That's what they see, light. But there are two readout techniques. One is the ionization. Okay, you ionize. When it hits, you rip off some electrons. You ionize, and then the electrons are moved, drifted upwards, hit the photomultipliers, and then produce a second light. That's called S2. So I have a S1 and S2 signal. Okay. And let me zoom in. So here it is. So you have a dark matter particle that comes in here, hits a xenon atom, and then the atom recoils and excites others, also causing a light. So it's not just one nucleus or one atom that you excite. You also can excite more than one atom. And these electrons, as soon as you excite them, you produce a light, and that's called S1. These electrons are drifted upwards, and once they reach the gas phase, they produce light. You pick that light from using photomultipliers, then you get an S2 signal. Therefore, you have an S1 signal here as a function of time, and then eventually have a S1 signal, and then eventually have a S2 signal. Okay? And you're gonna see that these time measurement between this peak and that peak is key to separate signal from background. And here what the real data looks like. So you have S1 signal, that's PET is like in photomultipliers units, and S2 signal. So all these dots are data points. So all the events they collected, I don't remember what was the exposure. I don't, let me see if I can read this paper. Hold on, let me improvise. This paper. So the file is too big now because of these figures. 23, 145, 29. 23.
147, 29.
147, 29, okay. Okay. Why is not, what's going on here? It removed the 20th archive.
ABS. The bar.
Let me open it. Okay, here it is. Oh, what? Did you see what it did?
Yes. Click over there.
That's what I did.
I mean, on the top.
Let me see. Let me do something. Okay. 2303.14729. So now you're reading the Xenon paper, and it must say the exposure. What happened? So it says here, you see, so radion and krypton are the intrinsic background sources, and they had here during the 1 tons times year exposure. See, so they didn't, well, they had 7 tons, so they did not search for WIMPs for a year because they had just 1 ton of exposure. Okay, so they have few months of exposure running direct detection experiment for a few months, and that gives them 1 ton times year of exposure, right? But they had 7 tons. If they had searched for a year, they had 7 tons, but they had just 1 ton. And you also have to take into account that it's not 7 ton they use, you just sum a fraction of this. Nearly, I think is 85% of the whole volume you have. That's the fiducial volume, takes out of 15%. And then you get 1 ton times year of exposure. Okay, let's go back. So that's what it is, 3D mapping. So as you see, what they are plotting here is just showing you how you get some, you see the blue events are like cornered in some region. The red events are cornered in a different region of the experiment, of the detector. See here, they say the mean +2 sigma counters for nuclear recoils and electron recoils are showing in blue and red. So nuclear recoils would be in blue and electron recoils in red. So nuclear recoils have a distribution which is different from electron recoils. And you see here, the measurement in energy is in keV nuclear recoil. They're already converting the electron recoil to nuclear recoil because they know the quenching factor that correlates one from the other. Okay? In this paper, they show what is the quenching factor is. Okay, well, I can extract it because they correlate the energy, the ionization energy, with the nuclear recoil energy, and the ratio of those two is the quenching factor. So they show this in the paper. So here it is. So look, a nuclear recoil gives you a time, a rising time, larger, a bit, well, it's not basically the same, but it's a bit larger than the electron recoil. It's basically, we can't see it, right? But the key thing is the following. So if you have a nuclear recoil, you don't strip off many electrons as you would do for electron recoils, and the S2 signal for electron recoils look much larger than this. But the precision these guys acquired are so amazing that they can discriminate nuclear electron recoils from nuclear recoils. I'm going to show you a plot later that's going to be really visible to you.
Why in general the ST2 signal with the signal 2 is larger than the first one?
Because why you have S2
larger than the first one?
This is just the amplitude of the light. So you rip off the electron, let's say you rip off some electrons. Just from getting the electrons out of the atom, you produce some light. But then these guys are drifted,
okay, so
and then hit the photomultipliers. So the photomultipliers will enhance this signal. Therefore, the amplitude of the photon light is larger for S2, right? Because that's the amplitude of the signal, the light.
So in this case,
like, for instance, the electrons are here. Let's say they are, well, it's not true, but they're at rest. Then they're stripped off. As soon as they're stripped off, they get some velocity, some acceleration, right? So the acceleration then emits light. That light is not much, but they are drifted within the electric field, and then hits the photomultipliers. Then the signals you expect, because you're drifting them with a force, with an electric field. And the S2 signal is proportional to the electric field you have, right? The S1 will be just proportional to, let's say, to the velocity of the incoming particle. Mm-hmm. So you can see in this figure here, look how it's insane to me. So this in photomultiplier units. So the electron recoil is here. And we have from the wall surface events, which is in green, is around here. I don't know if you can see it. Hold on, if I can change the color. Yes. The green is around there. It's all the way here. There. And there's the WIMP one, the one in red. So it's this one. And they say the region at which they have a better handle at discriminating WIMP or dark matter signal from other sources is this one delimited in dashed. That's the one. So if the signals you observe from S1, S2 have to be within certain range for you to discriminate signal from background. What I'm saying is, if let's say that you observe a dark matter signal, but it somehow is there around here in the blue, you simply say, I throw away all these events because I can't say. So we could have seen dark matter signals there, but I'm going to throw them away because I can't say whether it's a WIMP or it's an electron recoil. Okay? But dark matter events could be happening there, but I can't tell the difference. So what? And that region of interest, they picked for 200 GeV dark matter mass. So let's see. Tell me.
Why there's
Because you overlay one figure with the other.
no, I mean even larger.
That I don't know. He's asking why there are some colors which are darker than the others. That I don't know.
I think it's related to the. I know. Usually it's related to confidence level.
Yeah, I don't remember now. Off the top of my head, I don't remember. So now let's understand how they derive a limit. Okay. All right, so you're looking at a region of the problem space, which let's say is around there. And then you count how many events leaked into that region. As you see here, some events, despite my discrimination power, some events still leaked into the region. See, this event leaked here. There's an event right there. There's an event like there. There's an event like there. There's an event like there, right? 1, 2, 3, 5 events. So I try to subtract all the background sources using the fact that they have different S2 and S2 ratio, S1 and S2 ratio. If I do all that, I know my background, I know how many neutrons are decaying to my detector. And then after I sum the total events I observed as a function minus the background using the discrimination power, and then I get some events which they say leaked. We have some events that leaked into the signal region. These events could be dark matter, okay? They could be, but they could also be within some statistical error background events, but could also be dark matter. And some events there, these blue ones, could also be dark matter, and could also be the one that closer to the signal region could also be a background event, right? So I have what I can say is I have some statistical confidence that these events in blue are not signal, and I have another statistical confidence that the events within the dark matter are not background events. So the way as you move upwards or to the right, just changes the statistical significance that you can discriminate signal from background. That's all that is, right? It's not 100% WIMPs, it's not 100% background. But the farther they are from the signal region, the more discriminating power I have to distinguish signal from background. Okay? All right. So they observe some events. As a result of these events that leaked into the signal region, my constraint on new physics becomes weaker because I saw some events. Let me try to explain to you. So the larger the scattering cross-section, the more events I observe, right? That's easy. But it's not a number, it's a function. It's not say, okay, if the sigma cross-section is this value, then observe this amount. No, depends on the dark matter mass as well. Okay? Okay, fine. So what happened is, let's say if a scattering cross-section of 10 to minus 45 centimeters squared. And I should, for a given dark matter mass, I should expect 3 events. And I haven't seen any. And so, wow, then if a 10 GeV dark matter is excluded from my analysis with a scattering cross-section of 10 to minus 45 with 95 confidence level. But if I observe 2 events or 1 event, I don't have the same statistical confidence that no dark matter, 10 GeV dark matter mass was there, right? Because I say I expect 3 events, observe none, then I have very strong constraining power. If I observe 1, I don't have the same confidence, right? So what the experiments do is the following. I will only report results with 95 confidence level. So if I cannot exclude dark matter of 10 GeV, and then I move upwards with 20, can I exclude it with 95? Yes. So then I can constrain only from 20 above. So when you have events leaking to your signal, region, weakens your power of constraining dark matter particle scattering cross-section and masses. Okay, the more events I have there leaked, well, if there are many events, then I say, wait, maybe I discovered something. But if the number is not consistent with 10 GeV dark matter particle, it's less, right? If it was a 10 GeV dark matter, I would see many events there in the signal region. But they just observe a few. So maybe I did, I know, something happened and I don't have an excellent control over the background, and some events are still leaking into the signal region. It means that as a result that I did not do a very excellent job at removing the background, then I have some events in the signal region, then my constraining power got worse. Make sense? Okay? And this conclusion I just told, the reasoning I just told you, serves for collider physics, for direct detection, for neutrino physics, for whatever. Okay? If the signal event, this dark matter model predicts 10 events, and I observed none, then I have these models excluded with 99 confidence level.
That's because in the case of, because this is a model definite experiment.
Sure. Mm-hmm.
If it doesn't, not necessarily I will have this kind of thing.
No, so they're assuming a WIMP.
Yeah, that's true. I mean, that's
so
right.
the limit has to depends on your hypothesis,
Yes,
which is a WIMP.
Exactly, because I'm building to find that particle.
Finding
but
that
if
part.
it's a model indefinite, I don't have this relation.
But there's no model in depth. So
Yes,
the measurement itself, that one is model indefinite. When I want to translate what you see in this figure to a WIMP, then you have to assume something. Okay?
The signals, yes.
Okay? So then you have to assume something. It's the same discussion I had for indirect detection the other day. Okay, the flux is a measurement, forget it. When you want to convert now to a cross-section, then it's something else. You have an assumption.
That's right, because sometimes we are always thinking that these experiments for dark matter direct detection, they are for WIMPs. But maybe
they are for anything.
They could get some kind of different.
That's why direct detection experiments reach a precision that they are now sensitive to neutrino sources. So dark matter experiments have become neutrino detectors as well. Because neutrinos are weakly interacting massive particles, the same, right? Not as massive, but okay, but they're still massive.
People usually say about this kind of neutrino fog, I think you will cover it, right?
What?
The neutrino fog.
I'm not sure.
So let's talk a little bit. I mean, for example, just a little bit. Yes, in this figure. Usually people say that this kind of neutrino fog would erase some kind of possible dark matter signal, because it would be hard to distinguish between them, and maybe just direction of the
dark matter flux.
Dark matter would be the But I mean, why wouldn't it be very similar to this kind of discussion that we are having here?
For neutrinos, yeah, the same.
So we could also have different energy, but different energy recoil in the case of neutrino and dark matter.
Yes, we would.
So it would be possible to distinguish it.
Up to a certain point. So it's not easy. It's non-trivial. So if you have the direct, so for instance, remember what the experience this one sees is light, right? Yeah. And then you say, how are you gonna distinguish a 10 GeV dark matter particle if it's non-relativistic with a neutrino which is basically 0.1 eV with a very high velocity? Because what you see at the end, you convert into energy.
Yes.
And the only thing you know is that that particle is neutral. You don't assume it to be non-relativistic.
But for example, in the case of neutrinos, we have the experiments for neutrinos. We have different ways to analyze what interaction produced that neutrino.
Because the Cherenkov detectors is different. This is not Cherenkov detector.
So I see. That's true.
Okay. And the Cherenkov detectors, they do measure the direction.
Yes, that's true.
So they're not measuring the direction. They just know which point of the detector it happened. They don't know the
It's
trace.
like a scalar field.
Okay. So let's go into deriving the limit. Okay, so we have reviewed how direct detection experiments measure some signals. And now let's see at the end of the day how they derive limits. So we have seen that the scattering rate is proportional to the scattering cross section. Scattering cross section. Dark matter nucleus. That's dark matter nucleus. Okay. The velocity distribution, the density of dark matter you have in your neighborhood. So if you have detectors at the sun location, so it depends on what is the density of dark matter around the sun location, which is known. Okay. And what is the dark matter mass? Okay. So once I measure this comes from, look at this. This is experiment, right? Yes, I'm recording. This experiment. And then, can you all see my screen? Yeah. But everybody's so quiet over there.
Yeah, I see.
Okay. So you have the scattering rate. I measured this experimental thing. This comes from astrophysics. This thing, let me do it more. Experiment. This comes from astrophysics. And this one comes from particle physics. You have to tell me what your model. And this one also comes from Astro. Okay? But there's one thing that I didn't mention that about this d sigma d. You're going to see that we also need some nuclear physics input. We'll see soon enough. Okay. So what I'm saying is, let's say we measure the one in black. We measure how many events we observed in a given time. Then if I plug in the Astro input, the only thing is left is to correlate the sigma d over the dark matter mass. Then I can place a limit on how large the region in green there can be to explain the DRD observed. Okay? That's why my limits on the particle physics side relies on sigma and mass, because I do this for each point of energy. Okay? For a given energy, what's sigma over mass? This. For this energy, what's the sigma over mass? This. For this energy, what's sigma over mass? And then I can cover all sigma over mass plane. Okay? So my limits at the end of the day will depend on, hold on. I want to create one more page. On page 21. Let me create one more page. Okay, my page 22 is free. Okay. So I have is, what I have at the end is a limit, sigma versus mass. Okay? That's what I have in here. And now let's go to some detail which I find it very fascinating. So before I discuss something else. So just remember, DRDE will rely, after I plug in everything, all the Astro stuff, on sigma over mass. Then what I'm going to do, I'm going to place a limit, an upper limit, on the sigma scattering cross section, and where everything above is excluded. Why? I cannot have sigma larger than certain value. Why? Because I measure DR. DR is, let's say, represent the number of events. I observe one event. I cannot have a cross section that produces more than one event within my error bar. I can have it small because it produces less than one event. Let's say half an event. Half an event is not because I observe half an event. It doesn't exist half an event, but it's normalized by some constants, right? That's what it means. That's why I have 0.5 events. No, there's no 0.5 events. It's just normalized by some constant, you get 0.5. So if I observe 10 events, then I can have a cross-section that produces at most 10 events. If I observe 2 events, I can have a scattering cross-section that produces at most 2 events, right? And this scattering, this DRD is just the scattering produced from dark matter. The total number of events observed is much larger than this DRDE because I have to plug in the background, right? So just remember, that's the number, the number of events is equal the number of events from dark matter plus the number of events from background. So this DR refers just to the dark matter component, okay? What I do, I observe 10 events. In the end, how many events I should expect from background? 8, okay. So dark matter can produce at most 2 events, period. And what is the cross-section that can produce 2 events? This one, for a given mass, and then do one by one. For this mass, that's a cross-section. For this mass, that's a cross-section. For this mass, this cross-section. For this mass, this cross-section. Then I place a limit on sigma v over mass that produce at most that's those 2 events. Okay? Fine. So now let's understand why the curves look like this. Let me go back to my blue. Let's understand the curve. Tell me. Say it.
So, what about my hypothesis different, for instance, an action, a relativistic particle?
Mm-hmm.
And you said, okay, the detector doesn't know about it, so...
Sure. So I can construct actions the same way.
Right. But have scattering the nucleus, there is some requirement for
Energy threshold. Mm-hmm.
So the detector is for non-relativistic particles?
No.
Oh,
No.
what is it?
No, the detector is meant to detect a required energy larger than some value. Period. Nothing else. So if your detector is field of particle is non-relativistic, it's relativistic, let's say, it's relativistic. The only thing it needs is to have an energy that deposits energy recoil larger than the energy threshold of the detector. That's all. As long as it produces, I can detect it. But the way I correlate this with this scattering cross-section changes. Okay? So that general formula I wrote in the beginning, this one is still valid. Okay? This won't change, whether it's relativistic or non-relativistic. It won't matter. This will still be there. If it is relativistic, the thing that's going to change is going to tell me what's f of v is. Because f of v is for non-relativistic particles. It's Maxwell-Boltzmann. Assumed to be Maxwell-Boltzmann throughout. If it's relativistic, then you have to tell me what your sigma v, your f of v is. Everything else continues to be the same. Okay? Sure. Now, this formula doesn't depend on what is the nature of the particle. But now, as I go on, I'm going to assume f of v is Maxwell-Boltzmann. I'm going to assume that the momentum transfer is small. But I haven't assumed that yet. I'm going to assume it soon enough. In 15 minutes, I'm going to assume this. But so far, I haven't assumed anything. I just assumed that the particle had enough energy to produce a signal. In this same paper that I just showed you, they had a follow-up paper where they placed a limit on action particles, which were not dark matter. See, look, these actions fall into a range where its mass and couplings with photons are not in that band for the WIMP dark matter, are outside. So dark matter detection experiments can probe axion-like particles whether they are dark matter or not. Okay? Just like neutrinos. But you have to tell me what is the density of those nearby objects, because it depends on the density here, right? What is this? Oh, there. What is this? I don't know. Well, you have to tell me if I want to constrain it, because it's linearly proportional to the number density, right? Okay, so let's understand the curve. The way it goes as follows. You've noticed that as I go to light masses, to small masses, at some point, the dark matter is so light that I cannot see it, because you produce an energy recoil which is smaller than the energy threshold, right? But this is not like, okay, 1 GeV I see it, 0.9 I won't see it. No, you have some confidence level, right? And it has some velocity distribution as well, right? So for 1 GeV dark matter particle, I see it. 0.9 I won't see it. No, you can have dark matters at the tail or the velocity distribution that will still produce a recoil, right? So it goes with the tail. It's less likely, but I can still see it. So what happens is, as I go to lighter particles, remember, everything above is excluded. So excluded. So what happens is, so at light dark matter particles, the limit weakens sharply, because that is much less likely to observe a dark matter particle 1 GeV, because I have to really reside in the tail of the velocity distribution, which is like exponentially like this, right? Goes like this, the FFV. I'm gonna do it and I'm gonna erase later. You have a tail and then go like this. So let's say I have to be in that region at the tail distribution to observe it, because then I have large velocities, and then I will still produce a signal, but it's less likely, much less likely. So that's why your sensitivity, the limit on the sigma is small. Why is it small? Well, it's harder for the dark matter particle to produce a signal. So my chance of excluding it is small. You just have to understand, the smaller the cross section, the weaker is my limit, right? So I say, look, I observed 10 events. And then what you're doing is you're tuning a mass, which is very hard. Let's say my limit is 10 to minus 45. Dark matter particle scattering cross section has to be smaller than 10 to minus 45. And then he's tuning a mass, which is very hard for dark matter to produce a signal that I can measure with a scattering cross section at 10 to minus 45. Because the scattering cross section depends just on the particle physics content, right? But the chances of me seeing that particle decreases as you move to lighter dark matter particles, because of the velocity distribution. You see? So it's, despite being particle physics related, but there's some astro thing embedded in your derivation of the limit, right? Because as go to lighter masses, it's less likely that any dark matter particle will produce a signal. Because if it does produce, then I detect it, and I haven't seen any, so I'm going to exclude it. Make sense? So you exclude. And then around there, at some point eventually, reaches a dip. I'm going to explain what that is, and then rises again. I'm going to explain this rise. So there's a region right here where the limit is really strong, and then rises again. The reason why it rises is not, so this one is related to the energy threshold. energy threshold. This one, so, and this one here has to do with the density, number density. I'm going to explain it. Number density. How so? So we've just noticed the scattering cross section depends on the scattering cross section of the mass, but also depends on the number density. That's why we had this rho over m, right? This m came from the number density being non-relativistic, right? So that's where the non-relativistic comes to. See? I assume to be non-relativistic the moment I put 1 over m. Right? But depends on the number density still. Right? If I put rho over m, then I assume it to be non-relativistic. Because if it were relativistic, it would depend on the temperature. Okay. So it was sigma, and then I put it number density, but number density is rho over m. So it depends on the number density. But as you see, the number density is rho of dark matter at the local neighborhood. So you say h, this naught with a dot in the middle, over the mass. So as I increase the dark matter mass, there are fewer dark matter particles around. So there are less events I expect to see because there are few dark matter particles with large masses. Fewer, there are fewer of them, fewer and fewer of them. So less and less events I'm going to see it. And then again, if I observe 10 events and dark matter expects to produce less than 10, I don't have constraining power. If it produces more than 10, I exclude it. If it produces just 2, what can I say? I can't say much because I observed 10 events. In our exercise was, I observed 10 events in total. I'm assuming 8 was from background, right? That was my example. So 2 dark matter can produce at most 2 events. Okay, that was our exercise. I can produce at most 2 events. But as the dark matter mass increases, the total number of events those heavy dark matter particles produce are linearly smaller and smaller. So I expect to be already below the 2. As I increase the mass, let's say 1 GeV dark matter particle produces 1 event. If I increase by a factor of 10, produces 1 over 10 events. Okay, so it's just increasing, keeping the scattering cross section to be the same. As I increase the mass, the chances of observing a dark matter particle in the local neighborhood decreases by the same factor, 1 over the mass. Okay, because it depends on the astrophysical distribution of dark matter particles in our halo, in our solar neighborhood. And that astrophysical dependence goes with 1 over m. Okay? Fine. So, and this one here in the middle, which is more sensitive. So this has to do with the reduced mass. So reduced mass is m chi times mn over m chi plus mn. So when the dark matter particle mass is roughly the same, the mass of my nucleus, xenon, germanium, whatever, let's say m chi equal mn, this goes m chi squared over twice m chi, which is m chi over 2. Okay? That's the, okay, fine, makes sense? So that's the sort of the maximum value I can find for the reduced mass. So for instance, if you take the, let me say, it's like you tuning, I don't have more pages? Yeah, I do. Okay, let's think of the following. Mu is equal m chi times mn over m chi plus mn. So let's pick different values. If m chi equal mn, then mu is equal m chi over 2, right? If m chi is much greater than mn, then mu is equal m chi times mn over m chi. This is equal mn, right? Fine. But remember, I assume m chi to be larger than mn, right? If m chi is much smaller than mn, then mu is equal m chi. Equal 1. Right? So look at this. So then you play. So you have smaller dark matter particle masses. So let's pick at numbers now. To me, it's much easier. So let's say I had a xenon nucleus, so 100 GeV. Let's say this guy is 100 GeV. Mn is 100 GeV. In my analysis, I assume Mn to be 100 GeV. And let's play with the masses. So this is 100. And my dark matter mass is 100. So this is 50 GeV, right? So now m chi is much larger than mn. So this equal mn. So this is also 100, right? And the last m chi, let me see. Mn much larger than mn. Then this case, mn is much larger than chi. I got m chi. So it's smaller, right? M chi is much smaller than mn. So let's get m chi was in this case 1 GeV. Then you get 1, right? Okay? Awesome. So what happened is, so when dark matter mass is too light, the reduced mass is small. And then as you go increasing the mass of the dark matter particle, you reach a value where m chi is very large, or mu the reduced mass is very large. So it came from 1, and then you increase in the dark matter mass. Increasing dark matter mass, increasing dark matter mass. At some points, reach 50, the reduced mass. Gets a large, 50 times larger. So I came from 1 GeV here. So I came from, I don't have any pages more. So let me increase one more page. Okay. Oh, it produced, sorry. Because it changed the version. When I updated, it moved. Now let me see if I can produce it. Before, let me see if it will go now. Yeah, fine. It didn't. Forget it. Okay, but it's gonna be clear anyways. So let me erase this thing. So we came with dark matter 1 GeV is here, 1 GeV. And then you start, at some point, the scattering cross section just by kinematics increases by a factor of 50, right? Because the scattering cross section depends on the reduced mass. Just by kinematics, I'm not changing anything else. Obviously, there are other things at play. I'm not discussing them. I'm just changing the kinematics, just increasing, running the dark matter mass. I'm increasing the dark matter mass, and goes from, the reduced mass goes from 1 to 50, and then the scattering cross section increases by 50. Okay? Okay, fine. And then it increases a lot. And then reaches a dip around here, because why? As the scattering cross section increased a lot, my constraint also increased a lot. That's why my limit goes way below when the dark matter mass is around the mass of the nucleus. See?
For each kind of
Exactly. So this dip, so will happen at different places depending on the mass of the target. Okay? Because different targets have different MN. Obviously, and then I increased from here to, this was like 1, and that's the 2. And then the third point of when the dark matter is too large than the MN. So mu is equal a constant, right? Depends just the mass of the nucleus. That's why for any direct detection experiment, doesn't matter which nucleus they have, they all have the same feature, which is rising up, because it doesn't matter what the dark matter mass is, it's just the mass of the nucleus. It's in all of them. For instance, what I'm trying to say is, look at this. It's more complicated than this, obviously. I'm just talking about kinematics. I have light dark matter particle. The scattering cross-section itself, just the particle physics side, is small. Okay? And then I have a less constraining power, right? Because the lighter, the smaller the cross-section, the theoretical cross-section, the weaker the constraints I have. Okay. I increase the dark matter mass, which is close around the nucleus mass. The cross-section, just the cross-section itself, particle physics side, increases a boost by a factor, a very large factor. Let's say it depends on the mass of the target. Okay, in our case, we picked to be 50. Okay. All right. Increases a lot, and then my constraining power increases a lot. And then as the dark matter mass becomes too large, much larger than the nucleus, so if MK is much larger than the nucleus, in our case, I picked a value to be 100. But if you just look at this equation here, look at this equation. If MK is much larger than the mass of the nucleus, much larger, I just get the mass of the nucleus, which is a constant, right? Whatever it is. Okay? And that will determine, so you have something increasing. So my constraining power is increasing as the dark matter mass is getting closer to the nucleus mass. At some point, it won't matter, right? So let's say there was no density, so it would just be a constant. As I increase the dark matter mass, the scattering cross-section will increase. However, then another effect takes in, which is as I increase the dark matter mass, the fewer dark matter particles I have around, and then rises up again. So this is the constraint, not a theoretical expectation value. Because the larger dark matter mass is, the less constraint, the weaker the constraints I impose. But at some point around the nucleus mass, that's where my constraint from the particle physics side is the largest. Okay? So the one in the middle is driven by particle physics. The one in the right is driven by astro. And the one in the left, here, this one is by astro, this one is by the technical, the experiment itself, and this one in the middle by kinematics. Okay? So one is experimental side, one is kinematics, the one in the right is astro. Okay? So the exclusion limits depends on 3 inputs: experimental side, kinematics, and astro. Okay? Okay, so I'm done for this part of direct detection. So I'll ask if there is any questions, please ask. If there's not, I'm gonna move to the 7th lecture. There's one thing I need to cover before we move to 7th lecture. One thing I forgot to mention is that I mentioned to you that I'm neglecting some things, so there's some things I didn't discuss, which is the form factor. So the scattering cross-section does not depend solely on particle physics. Does also depend on nuclear physics. Why? It's the same as colliders or accelerators. So you have a particle coming in, and you learn this in quantum mechanics or quantum field theory. So if you have a particle or reaching, colliding, or scattering a nucleus, if the wavelength of that particle is comparable to this radius of that atom, then you have quantum effects at place, right? Because it's sort of, you're kind of seeing what's inside the atom. If the wavelength of the particle is much larger than the radius of your target, then it's like, to me, it's like we just jump the atom. You'll see just the atom as a whole. You won't see what's inside of the atom. Okay? As the wavelength decreases enough, then you're going to see the whole atom, what is inside the atom. You're not going to scatter with the atom as a whole. You're going to scatter with everything inside the atom. So let's say you have a neutron, and then you have the wavelength of a particle is much larger than the size of the neutron. Then you just see the neutron. If the wavelength of the incoming particle is very, very small, then you're not going to see the neutron. You're going to see the quarks that are inside the neutron. Okay? But the wavelength is inversely proportional to the energy or to the momentum. So the larger energies, large velocities, means that I can see the whole thing. I can see what's inside the atom, inside the nucleus, or inside the neutron. Okay? That's why, for instance, when we want to probe quarks, we need the high energy colliders because we want to see what's inside. Smaller energy accelerators just see the whole nucleus as a whole. Okay? All right, so we want to test fundamental particles. That's why we need large energy accelerators, because we want to test the fundamental parts, ingredients of the particles, right? So, and this is embedded in the form factor. So the form factor just tells you how the scattering takes place as you increase the momentum of the incoming particle. And this form factor, which is called the Woods form factor, which is just consider they treat the nucleus as a shell with some I'm not even blanking the word, with some diameter, or not diameter, some thickness. So instead of being a shell, it's a shell with some thickness. That's how they treat the nucleus. That came from where? It was like out of nowhere? No, they just took this sample and see if it would reproduce the nuclear data. And say, okay, if you assume that when a particle comes in and sees the whole atom, the nucleus as a whole, how can I describe the interaction with the nucleus? If that nucleus was treated as a shell with some thickness A. That's how you treat that, the interaction when you have an incoming particle with a very large momentum. So this form factor you can see here in this figure, so it's equal 1. So let's say if d sigma dE is d sigma naught dE times the form factor. It's just a notation, okay? F squared. So this naught refers to the scattering cross-section removing the form factor dependence. So d sigma naught dE, remember, it's just removing the form factor. So when you have low energy recoil, so if the incoming dark matter particle has a small momentum transfer, induces a small momentum transfer, then there's no form factor. You just see the whole nucleus as a whole. As the velocity of the incoming particle increases, so let's say you're at the tail of the velocity Maxwell-Boltzmann distribution, then you start seeing what is inside the nucleus, and then the scattering becomes inelastic instead of elastic. Okay? So you have to take into account, because the velocity is not a constant, it's not one value, it has a velocity distribution. Therefore, the scattering cross-section can become inelastic for large momentum transfer, which is the 7th conclusion that I pointed out in the very beginning of today's lecture. And obviously, that depends on the target of the nucleus, because what people did was, nuclear physicists, they took different targets, germanium, sodium, the ones that are used for direct detection experiments. They did this in Germany. So they picked some different values and put a neutron source and bump into the material to see how the material would interact as you increase, would respond, as you increase the energy of the nucleus source, the neutron source. So you increase the neutron source energy, increasing and bump into the material, and then you see how the material responds, and then it's how you sort of parameterize the form factor of that target as a function of energy. Okay? And as the energy for dark matter is not large, so it's not also very hard to have a neutron source with low energies. If it was very high energy, that would be tricky. But for small energies, it's not so hard. Okay? Hold on, Jacinto! Jacinto is falling asleep here.
Almost died.
So, both the scenario of most dark matter is on the center of the galaxy, dark matter A, annihilation, matter B. Dark matter B is
So it's inelastic.
yes. So we have
He's asking about boosted dark matter.
different density, local density, and different relation with mass. And the distribution of velocity is also different. That means what isotropic from the center, I think.
Yeah.
And these form factors also apply to larger energies, or
Yeah, this form factors has nothing to do with what's the nature of dark matter. Has just to do with the target and the energy of the recoil. So it has nothing to do with dark matter. This thing has nothing to do with dark matter.
the scenario I have to apply this form factor in the regime that I am interested. Again, I have some details, but the same strategy.
The key thing is what people from boosted dark matter do. Let me tell you. So they pick a dark matter mass at which most likely the momentum transfer or the energy recoil resides in the dip. So if you picked a dark matter mass, when you take into account the most likely velocity of a Maxwell-Boltzmann distribution or whatever distribution they have resides right here, the scattering cross-section is very small, right? Therefore, the constraint you have is very small. So for heavy dark matter particle masses, for heavy masses, I can tune the mass to be so large that the scattering cross-section became inelastic. The scattering process became inelastic. And then if I'm right here, around there in the neighborhood, right, the velocity is not a constant, there's some velocity distribution, then the scattering cross-section becomes small. However, for the WIMP-like particles, most of the scales reside around here. That's the WIMP. So it's nearly elastic. We won't change much. I know. There is no dip. Imagine the scattering cross-section being decreasing, okay, but then eventually it drops orders of magnitude. That has to do with nuclear physics.
But that's for the air detection experiment. Okay, so in these boosted scenarios, we say, let's try to reuse an neutrino detector, like Okay, that's different strategies, different approach.
Everything. Boosted dark matter was created to make neutrino detectors look good.
I see. But that's other.
To be honest, I would say this, but it's fair, okay? It's just showing that there's, depending on what's the nature of dark matter, you can make neutrino detectors to be a promised laboratory for dark matter, which is true for many other cases besides boosted dark matter. Okay? It's true. It just it's just showing that, again, there is a strong overlap between neutrino physics and dark matter nowadays. Okay. Okay, fine. That's what the last thing I wanted to say about these lectures. Okay, so we learned seven lessons, and now let's dive into the scattering cross-section. So let's say, I'm gonna assume that the scattering cross-section can be separated spin-dependent and spin-dependent. I'm picking a model where the spin-dependent part is not at all related to the spin-dependent part. I'm going to show you what the spin-dependent and spin-dependent means. So I'm gonna rewrite the sigma DE as the scattering cross section naught. Remember, this naught here refers to I'm removing, separating the form factor from the scattering cross section from the particle physics side. This sigma would be the total sigma, and this factor here is just a normalization. Okay, I'm just rewriting the scattering cross section. This has to do with how I define the scattering cross section in the beginning. So from here, I can rewrite this as a function of the momentum instead of energy, as energy is momentum squared. Momentum squared depends on the velocity squared. And then once I do in terms of momentum, and then I have to, again, put this v squared over here because I separated, see, there's a function of momentum now. So sigma 0 has no energy dependence. The whole energy dependence is embedded in the f of v, off of f of q, the momentum transfer. Then this q is no energy. Q and energy are not the same. There's some reduced mass and v squared dependence relating each other. That's why I normalize by mu squared v squared. Anyway, it's just a way of rewriting this scattering cross section, but that's not the key thing here. The key thing is that I'm separating spin dependent from spin dependent. And you're gonna see often people talking about spin independent and spin dependent scattering cross section. That happens indeed for the trivial cases where dark matter particles have trivial, let's say vanilla Lagrangians, and I'm gonna show you some of them. In general, this is not true. This spin independent and spin dependent definition is not correct, but it's an approximation. And spin independent means spin, there is no dependence on the spin of the target. Spin dependence, there is spin dependence on the target. So the nucleus might have a spin. If there is a coupling, if my scattering depends on the spin of my target, then I call it spin dependent scattering. And if it does not depend on the spin of the target, I call it spin independent. Has nothing to do with the spin of the dark matter particle, rather on the spin of the target. Okay? However, I emphasize, in some general cases, I might have a scattering cross section that does depend on the spin of the dark matter particle. I might also have a scattering cross section that depends on the spin of both, and I can also have a scattering cross section where it depends just on the spin of the dark matter particle and not spin of the target, and vice versa in more general cases. And you have to include all of them. Okay. Luckily, so in the vanilla cases, we can rely on micromegas. Micromegas does compute the scattering cross section for the vanilla cases, which are the ones I'm going to cover. For the other non-trivial cases, micromegas does not include it. So if you have a more complicated model, sorry, but you cannot use micromegas for this. Okay, you have to really compute the scattering cross section yourself. Fortunately, for dark matter, WIMP-like dark matter, non-relativistic dark matter, the way how you compute it has been done. For all cases you can imagine, you just have to they define some parameters. Nuclear physicists, okay, did this. They define some parameters. You just have to correlate. Okay, this is my particle physics model, and match what your particle physics parameters, mass, coupling, whatever, matches to whatever they define in nuclear physics. Okay. All right. So let's discuss the spin independent scattering cross section. So I want to emphasize that what I'm calling scattering cross section from now on refers to scattering cross section H sigma naught, not the sigma naught. I'm gonna neglect the nuclear form factor for now. Okay, from now on I'm gonna neglect it. So I'm gonna call it sigma SE, spin dependent, but it's actually sigma naught SE. So the dark matter nucleus spin dependent scattering cross section, remember, the sigma naught SE. So now let's think of this case. So that's more our language. So I take a Lagrangian, write down the dark matter interaction, which refers to chi, represented by chi, coupling to quarks, Q. And as you know, let's think of an example. So let's say in the standard model, I have a Lagrangian which is like this. I have E bar E in the Higgs, and that interaction is proportional to ME over V, right? That happens for zero Lagrangian, where the Higgs couples to electrons, right? You also have the same for quarks, where it is MQ. So this is a Higgs, okay? Then if by any chance then I'm going to write the same. If my dark matter particle does have an interaction with the Higgs, which is proportional to m chi over some VAV, chi bar chi, and the Higgs. I'm just replacing Q by chi. And then these two Lagrangians could be represented in a compact form as chi bar chi, Q bar Q, where everything in the middle is the product of these two couplings. Okay? So this is called an effective field theory. However, notice the energy. This is 3/2, 3/2, 3/2. If my car is a Fermi, 3/2. Okay? Is a Fermi, or if it's a scalar, in my case. If this is a scalar, that would be chi daga or chi. Okay? If chi is a scalar, I would call it chi daga, right? Or chi. But it won't matter if it's a scalar, it's a Fermi. So if it's a Fermi, it's 3/2, 3/2, 3/2, and 3/2. So it has dimension 6. So it has dimension 6. My Lagrangian should be divided by the mass squared of the mediator, which would be the Higgs mass. So it would be 1 over mh squared. So it's a way to plus some constant. Which constant is this? This is v squared, right? I'm gonna rewrite it. You're gonna see it. Hold on. Let me zoom in. So I can rewrite this. I put the chi bar h. So I can rewrite this Lagrangian as, you're gonna see it as m chi mq v squared times h squared, and then chi bar chi q bar q. So this thing we had already at the Lagrangian level, and then I suppressed by the mediator squared, which is the mediator of these interactions that I had in the first place. So this is a dimension 6 operator, okay, divided by the mediator squared. So this is called L effective, or effective Lagrangian, that describes the interaction for these Lagrangians, QQ bar H, QQ bar H, and chi bar chi H. Okay? That's called effective Lagrangian. As you see here, when I write, it's like the beta decay. When I had the W boson, and the W boson was just 1 over MW. I did not write gamma mu 1 minus gamma 5. I didn't write this. So didn't know that W boson exists in the beta decay era. So I just assumed that was 1 over lambda, and that lambda turned out to be the W boson. So it's the same way. I don't know what's the particle which is mediating the interaction between dark matter particles and the standard matter particles. I don't know. So I'm going to call it this particle H. I could call this particle lambda, whatever, mz prime, whatever. This mh refers that just because you're taking to be the Higgs, but it could be some lambda scale. Lambda is some energy scale that you don't know, which is related to the mass of the mediator that mediates interaction between the dark sector and the visible sector, the standard matter particle and the dark particle. Okay, so focusing on the scalar case, if dark matter is a scalar field, let's say chi daga chi, q bar q is a scalar, you can compute the amplitude for this diagram. So you would have chi going to q bar. If chi is a scalar, let's say chi daga going to q bar, I compute the amplitude. This is easy. And then you compute the scattering cross section between these two. So let me rewrite like this. because it's a scattering. Let me write like this. You complete the scattering cross section, then you can show that the scattering cross section between the dark matter and quarks is something, but the one they measure is not dark matter interaction with quarks, but dark matter interaction with nucleus, which is different, very different. What these guys, nuclear physicists, have done is, okay, if I have something which is a scalar and interacts with a nucleus, how does that nucleus respond? I'll respond with some factors, some form factors going from quark level to the nucleus level. And this translation from quark level to nucleus level is called, what the things I'm going to show you today is called the dark matter nucleus cross section. Okay, and they have to relate somehow with some nuclear physics stuff, and also the quark level particle physics Lagrangian. So the dark matter nucleus is scattering cross section. Remember, I'm removing the form factor. I'm not taking into account the form factor of being elastic. I'm not taking into account this. Yes, I'm taking into account nuclear physics, but not the fact that that scattering has some momentum dependence. I'm not taking that into account, okay? I'm just taking to the fact that I'm converting a scattering of quarks to a scattering of nucleus. That's all I'm doing. I'm not saying whether this scattering is inelastic or elastic. I'm not doing that part. That part is encoded in the FQ, right? So then you can show, I have this calculation explicitly done. How you go from here, this Lagrangian, up to this one below. I have this explicitly done for this clear case. I can share with you. I will try to share. Write down the notes, an extra note, and then write down the explicit derivation of this. I haven't seen this in books, so I did it for the first time when I was writing my first paper on dark matter. Anyway, so this scattering cross section, not, depends on the reduced mass between the dark matter particle and the nucleus, the amount of protons you have in the nucleus, Z, Fp, I'm going to show what Fp is, plus A, the atomic mass, minus Z, the atomic number, and Fn, everything squared. So Fp is saying, look, I have dark matter particles interacting with quarks. That's what it is here, with quarks, right? U, D, whatever quarks. And how you go from quarks to a neutron, and from a neutron to a nucleus. So there are two steps. And it has been shown that the interaction from quark level to a nucleus level, what you have to do if the interaction is a scalar mediator, which is this scalar here, there is no Lorentz, right? Yeah. In the component there's no Lorentz matrix. So if it's a scalar, if the interaction between quarks is a scalar, is identity, the whatever is coming in is interacting with the whole nucleus if you just sum the amount of nucleons you have. So it depends on the number of neutrons and depends on the number of protons you have. That's all. Okay? So this is the number of neutrons, right? This thing. So it depends on the number of neutrons times how it couples to neutrons. Depends on the number of protons times the number of protons. The coupling with protons. And what is the coupling with protons? Well, proton has two U and one D. So it's twice the coupling with U minus plus one coupling with the D. And the neutrons is just, reversing. Okay? 1 and DD. We just sum the couplings. But do I know these couplings? Yes, my Lagrangian I have. Let's say I have in my model Q, dagger, Q, U bar. Is lambda 1. But my model is lambda 2, Q, dagger, Q, D bar. Then I know the couplings with U and D. So it's the coupling with protons would be 2 lambda 1 plus lambda 2. With neutrons, it will be 2 lambda 2 plus lambda 1. See? Make sense? Okay. So, and this is FP. Okay, but when you have to go to the nucleus element, what you do is the following. This FP, hold on. Yeah. This FP, how the dark matter couples to protons, FP, depends on the mass of the proton. Okay. And this alpha Q is the coupling of a given quark, U, S, and D, divided by the mass of that quark. So you have sum. I can write down like this. Let me erase this. I can erase this. I can erase it. This Q is summing in U, S, and D. This alpha is the coupling of S, U, S, and D. FT is a parameterization parameter, is a parameterization that came from nuclear physics, which was translating the coupling from up, as strange and down quarks to a proton. And this term here on the right is when you take into account loop effects, where you have couplings with gluons also included. Okay? Why? Because you have this interaction here, chi, let's say, well, it's a Fermi scalar, whatever. And then you have a scalar here, and then you have a loop of quarks, and quarks, and this comes gluons and gluons. And that's the nucleus. So this thing has to do with this coupling here. Okay? And this one is this term right here, nucleus. So the first one is a tree level. The second one is a loop level contribution with gluons.
And tree level actually cannot happen because that would be not weakly interacting but strong.
Yeah, it does not happen at tree level because I'm assuming to be weakly interacting massive particle. But at loop level, it might happen. In the end of the day, the contribution is not very large. Okay, but you can still plug that in and it won't change much. So this is tree level, is loop level. This is for the scalar case. For the vector case, it's easy. It's just what I just told you before. I don't need to compute all this whole thing. I just sum. What is the coupling with protons if the interaction was a vector one? I won't do explicitly here today. So if it was gamma mu here and gamma mu there, gamma mu and gamma mu, for instance, what's this one? It's here. Sorry, it's there. This one. If my interaction was like this, the easy part, that's why I also love Z primes, because Z prime bosons will have induced a vector current like this. And then I don't need to compute FP and FN like this way. I just say how many, well, a proton has 2U and 1D. I just sum the couplings of U and plus one with the neutron. And D would be twice the coupling with D plus one with the neutron. So, and I know it at the Lagrangian level. I have my Lagrangian, I have written my model, right? So I know the couplings I chose. So I just sum the couplings I already know how to compute the scattering cross section. So it's very easy in this sense. For the scalar case, it's less trivial because you have to plug that in. And these FT couplings are constants and are given by nuclear physics, okay? You're just saying at the end of the day is that if something is interacting with quarks in the middle, in your nucleus, and this current is scalar, like, then you have to sum the number of protons and the sum of neutrons, but you have to also include some other effects, and these other effects from nuclear physics are proportional to FT, and FT is not the same for all quarks, and have to also include some loop level diagrams, and you sum all that up, sum all of them. Anyways, but I want to, that's not the key thing. The key thing is the following. So at the Lagrangian level in the particle physics model, I go to the quark level scattering cross section to the nucleus scattering cross section, and to go from one to the other, what I have to do, there's R missing here, quark. When I go from here to here, has nothing to do with that form factor. The only thing it has to do is comes from nuclear physics. Nuclear physics studies. Okay? And these studies have been done already for all interactions you can think of, all of them. All the 16 combinations of Lorentz matrices, all of them have been done for all of them. And not a long time ago. I think the first time they did it was in 2016. So we are talking about a field that has been computed this in 2016. Okay? Not that long ago. Huh? Yeah, it's Liam Fitzpatrick. I did not download it. It's from Liam Fitzpatrick. Liam Fitzpatrick paper. It's one of the most well-studied papers in dark matter for the past, since then, 2015, 2016. As he wrote a paper with some nuclear physicists guys, and they did this. So the funny thing is they have done it not for dark matter, for many cases. And now they include all the possibilities for dark matter, all Lorentz possibilities, Lorentz combinations of operators, matrices, and they compact everything into one paper. And that became like a Bible for direct detection experiments. Okay, and these values are here, so I quoted some values, so you don't have to compute them. So what I want to see is emphasize the following. Look at this. Look at this formula. So I start with some Lagrangian that has some couplings with quarks. These alpha are here. See? These alpha are here. The only thing I need to do is plug in some constants which are given already. The mass of the quarks I already know. They are tabulated. So the mass of the quarks I know, these constants I know, I have to plug in just the constants of my theory, which I know. I was the one who wrote the theory, so I know those couplings. Just plugging that in, I know what Fp is, Fn is. I know the target. Yes, I know its atomic mass, and I know its atomic number. Then I compute the scattering cross-section. You see? So I know the couplings, alpha, and then I got from nuclear physics this one. I plug back into this equation. I know Fp and Fn. I know the target, so I know A and Z for that target. Then I know the dark matter nucleus scattering cross-section for any target you can think of, for any Lorentz combination. Okay. So what I want to discuss now, something to conclude today's lecture, which is taking longer than I imagined, is that, look at this. As you can see here, this FT from nuclear physics, they concluded that if the dark matter has, a scalar or vector-like interaction with quarks, doesn't matter whether dark matter couples to a neutron or with a proton. At the nuclear level is the same. Okay? If dark matter happens at the Lagrangian level, happens to have the same coupling with neutrons, and the same coupling with quarks, with up quarks and down quarks, if it has the same, so it means has the same coupling with neutrons, the same coupling with protons. When you go from quark level to the nucleus level, the nuclear physics does not include any difference between quarks and between neutrons and protons. Let me repeat what I said. So if you interact with an up quark or a down quark at the nuclear level, it means the same thing, as long as you couple with them the same way. If you couple with U and D in the same way, when you go from quark level to the nucleus level, it means the same thing. if it's spin independent. Okay, so it means is the constant for nuclear physics for protons and neutrons are the same if it's spin independent. Okay, so if it is the same, then the only thing that matters is how many protons and how many neutrons you have in your nucleus. Because if they couple to protons and neutrons the same way, I just have to know how many protons and neutrons they have, because they couple the same way. Or in other words, the atomic mass. Now look at this Lagrangian. Look at this scattering cross-section, just to conclude today's lecture. So this dark matter scattering cross-section with a nucleus depends on reduced mass, okay. The coupling with protons and the coupling with neutrons. I'm saying if it's spin dependent and the dark matter couples with up quarks and down quarks in the same way, so this F alpha here are the same, if they are the same. It's not necessarily true, okay? Let's think an example. The Z boson does not couple to up quarks and down quarks in the same way. Does not. There's a difference. There's an isospin difference. One is plus 1/2, the other one is minus 1/2. That's induced a change in the neutral current. The neutral current for U quarks is different from the neutral current for down quarks. Yeah, they're different by some constant. Okay? It's not the same. You can compute it. Take the Lagrangian for Z boson. It does not couple with the same with U up quarks and down quarks. It's not the same. It's different. By some number, not large, but it's different. But I'm assuming it's the same. If it is the same, then Fp is equal to Fn. Or let's assume it's not precisely the same, but it's roughly the same. If it's roughly the same, then Fp is equal to Fn. So the way it couples to protons is the same way it couples to neutron. If this is true, then the scattering cross section will grow with Fna squared. Look at here. So if Fp is equal to Fn, then this part here of the scattering cross section will cancel out with this one. You just get some Fa squared, right? Right there. Okay. So I'm gonna write like this, and then I erase this whole thing. Yeah, that's the one. Just need to find the paper I was talking about. So I got just this one. Therefore, wait, I have to write as A. So I'll get proportion to A Fn squared or Fp squared, doesn't matter, because I'm assuming them to be the same. Then I conclude something which you're gonna see in many, many dark matter papers. They will not recall this. You just say it's true, and then you have to figure out why. They say, you're gonna see in many conferences, hey, I'm probing spin-dependent dark matter scattering, which is proportional to the A squared, which is proportional to A squared, which is proportional to the atomic mass squared. That's it. They are saying this, but they are assuming that the coupling with protons and neutrons to be the same. Okay? And that's really interesting because the experimental results today from direct detection experiments, such as the paper I'm going to show you from Xenon March this year, they report their limits assuming Fp equal Fn. So the report experimental limit based on Fp equal Fn as a function of dark matter mass, that plane, assuming that. So that means that's not true for all models. It's spin-dependent models. Just true for spin-independent models in which Fp equal Fn. So there are many theoretical assumptions in that limit. And in models at which the Fp is different from Fn, as happens for many scalar models, scalar mediated models, isospin violation models, Z-like particles, because the Z does not couple to up quarks and down quarks in the same way. So if you have a model which is like a Z boson, you cannot use Xenon limit. You have to readapt, recast their limits to apply to your model.
I mean, the Say again.
So they have a limit. Scattering cross section. Just a second, Patricia.
Yes, I think the part of the FP equal F, and I got it.
Here. So here's the paper. Let's write it. Let's show it. They report a limit. WIMP nucleon cross section. So they're assuming that the nucleon, so protons and neutrons are just a nucleon. They are the same. That's the limit they found. So everything above the black curve will be excluded. If you have a model which you have a cross section above the black solid curve, will be excluded. Assuming FP equal Fn. If in your model you have a spin independent model, so you work out to see it's not dependent on the spin, fine. Can you use that limit? Not necessarily. Is in your model the coupling of dark matter with up quarks is the same of down quarks? If it's different, you have to recast that limit, taking into account that the ratio is different, is not 1. It's like they assume to be the same, right? So as you saw, that sigma for them is just a squared times f. But in your case, it's not. Yours is Fn, you have a minus z, blah, 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 that depends. So you have to compute yours and see the ratio between them, and then redo the limits, rescale up and down their limits. You see? So you have to do for your own model. So the experimental limit from xenon cannot be used blindly to any spin-dependent dark matter models. Cannot. Depends on your model.
Usually in the models that we have new abelian symmetry, usually we have
they are
that
not
Z
the same.
prime. Usually you assume that Z prime couples equally to.
It's a vector-like coupling,
It's a vector line.
and then it's the same.
Yes. But yeah, we have. Yes.
For instance, the model of two Higgs doublet model, if you want extra gauge symmetry, they are not the
They're
same.
not the same.
But they report nucleon. So what, take a step back from this assumption?
No, so the WIMP nucleon, what they're doing is so for instance, the WIMP nucleus cross section is this one. And they call this one in blue the WIMP nucleon. So the only difference between them here is divided by a squared. N times mu. See, here it is. Here it is.
This F is.
So you have this cross. So let me see if I can
Yes.
got this whole thing. Come on. Oh, I don't have space. Let me write. Well, I have only 4 pages. Okay, now let me see if I can. Okay. Start new pages. Let me see now. 4. Okay, now I went. Okay, so I had sigma dark matter nucleus was 1 over me squared v squared, right? Me squared over pi. Me squared over pi. Fp z plus a minus n, a minus z, fn, everything is squared. So what they do is they assume Fp equal Fn, okay? Then they get sigma dark matter nucleus. That's what they do. Equal me squared over pi squared, Fn squared, a squared, right? Okay? And they call this thing sigma dark matter nucleon. Okay? And there is something else, but let me correct something here. Hold on. they multiply by mu dark matter nucleon divided by mu squared dark matter nucleon, or proton neutron. They have basically the same mass, right? Nucleon, not neutron. This is neutron or particle, neutron or proton. That's nucleus. This mu here is dark matter nucleus, right? But this one I'm saying dark matter nucleon. Okay? And then what they do is the following. So then they divide sigma dark matter nucleon is equal, they do this. Is Fn squared over pi squared Fn squared A squared times mu squared dark matter nucleon. That's the dark matter nucleon scattering cross section. That is mu squared. This one. See? It depends on just on the nucleon mass, which is 939 MeV. This does not depend on the nucleus, except for A squared. Hold on, this thing is not here. That's what it is. So the nucleus dependence is extracted out of the dark matter nucleon scattering. So as you see here, this is just particle physics, right? Dark matter mass and then nucleon, the proton mass, as we know. Fn is just particle physics. So this is dark matter nucleon. But to convert to this from here, you had to assume it's not from here. You have to go compare this one with this one. But in order to do so, I had to assume Fp equal Fn, which is not necessarily true. So what you do is you complete explicitly what's dark matter nucleus. So xenon, how many xenon is 131? How many protons, how many neutrons they have? This amount, I plug in Z and A minus Z. Okay? In my model, I know how to compute Fp. I know how to compute Fn. Right? Then I know it. And then I reuse this normalization, what they call dark matter nucleon. So they found dark matter nucleon for them was this value. For mine was 10 times that. So then I have to rescale that limit by a factor of 10.
So you have, for instance, each interaction with ups and downs.
It's the same. It's the same.
Okay.
Yeah, it's the same, basically. Then there's no difference. And why I'm saying this, because you have models where you have a flavor Higgs, where the Higgs couples differently with different flavors of quarks, couples more with a new Higgs, a new scalar, couples more with up quarks than with down quarks. You have Z primes where the coupling with generations are different, a generation dependent. So I have first family couples in one way, second generation in a different way. So the coupling with quarks and D could be also be different. Okay, and there is also some flavor dependence as well. Depends on if either spin plus 1/2 minus 1/2. The couples are also in different ways. And they realize that's not very hard because the Z boson does this, right? If you remember, the Z boson neutral current depends on the charge of the particle, but it also depends on the isospin of the particle. And the isospin for up quarks and down quarks are different. That's why the Z couples differently with up quarks and down quarks. If dark matter resembles like a Z boson, you cannot take at face value the xenon 1-ton bound or any direct detection bound. And we have been complaining to experimentalists strongly, I would say, hey, your bound, sorry, but it doesn't make much of a sense. That's not what you should report. You should report to us what's the dark matter nucleus scattering cross section and let us do the job. We do it and say, Fernando, if we do this, half of the dark matter community won't know what to do with this. What are you saying? Yeah. Do you think the dark matter physicists, well, they're not dark matter physicists, they are particle physicists who are trying to do some dark matter. They don't know this detail you're talking about. They just think it's the same. They don't know this level of detail of converting dark matter nucleus to dark matter nucleon cross-section. They don't know this. They'll just use the wrong result. So what we could do is, and also there's some political things, such as if they do this, they won't fit into a letter, PRL letter, 4 pages long. So, but okay, fine, then submit a supplemental material with your publication, appendix with the whole results. It's fine. I mean, keep it in 4 pages, just plot the dark matter nucleon cross sections, fine. Put a supplemental material. Or even better, provide as a software or a likelihood function where I can just plug in my model, my FP and FN of my model, and the likelihood function will derive by, for me, what the bound on sigma is. We've been complaining this for many years. And luckily, last year, for the first time in the history of dark matter physics, xenon collaboration or any direct detection collaboration reported a best fit function where you can plug in your FP and FN and get yourself the bound on sigma. Then I don't have to redo this math for every model. Okay, so that's the details hidden in dark matter physics, which is often overlooked when a particle physicist is trying to do dark matter physics. They just think, but that's the bound there. You see, you notice for indirect detection there are caveats. For direct detection there are caveats. You cannot take the value of a bound and say, hey, this is the bound. Your model is excluded. No, it's not excluded. Why is it excluded? Depends on the model. Okay, so you have to know the details. And just to finish, now it's, wow, almost 2 hours of lecture already. That this band here, as seen in the plot, you have 1 sigma and 2 sigma band. So what it means is, so for instance, take it the black curve. The black curve is just the one that's the observed limit. So it means is, if you have a model in which the theoretical model has a cross section within this band, is not excluded in 2 sigma. So if I have a model is up here, right here, let me zoom in. So if I have a model which is around there, right, this corner right here, is not excluded, despite having a limit in the black curve. This is a statistical significance. Okay? This statistical bound has an error. My error, I can still have a signal within the error. Okay? If it's larger than the error, then I'm excluded. Then I'll be excluded. But if I'm within the error, so say, at the end of the day, this goes about the number of events. They observed some two events was consistent with dark matter. That was the example we had, right? But it's not 2, it's 2 plus minus 1. So if my model predicts 3 events, can you exclude it? No, because within the error is consistent with the measurement. See, it's 2 plus minus 1. So it's still 1, it's still consistent with the measurement. So I cannot exclude it. You can say certain confidence level, it might be excluded, but you cannot say this is excluded. No, you can't say this. Right? Can you still be consistent? Right? Okay.
Suppose that I wrongly assume that event.
Let me just interrupt you for a second. So is there any questions here? Are there any questions? Sorry guys, it was too long today, but there was a lot to cover. So for those of you who are still listening, we're gonna have dark matter and neutrino school at ICTP Safer in July next year, and I'm one of the organizers. And you're gonna have 3 lectures on dark matter of 1 hour each. So now you can know how much detail we are going into in these 10 lectures, because I doubt that you're going to see all these details in 3 lectures of 1 hour related to dark matter. But that's what it is. So, okay, so if there are any questions here in the audience, I'm going to stop the recording and we move on to tomorrow at 9. because there is a holiday on Thursday, and then I'm gonna travel on Thursday morning. That's why we won't have lectures on Thursday, neither Friday. Okay, that's why I want to do it tomorrow and Wednesday morning. So tomorrow at 9, Wednesday at 10. And tomorrow is at 9 because at 10:50 I have to give lectures. So I'm gonna be lecturing from 9 to 9:30, 10:50 to 3 p.m. Okay? All right, guys. Bye. Thanks for listening and for your patience.
Bye-bye.
Bye.